Today on How It's Made. Gel caps. Playground spring riders. Frozen pancakes. And natural rubber. Liquid medication used to always come in a bottle, and you had to pour your dose, with a steady hand, into a spoon. Today, many medications and supplements come inside small food-safe casings that are easy to swallow and portable. Soft gel capsules. Many types of products come in gel capsules, from prescription drugs to health supplements such as fish oils. Many of these medicine fills go bad if exposed to oxygen, so the gel cap, besides being convenient, also serves as a protective barrier. Every ingredient in both the gel cap and the medicine fill inside undergoes extensive testing for purity. The first test phase checks for bacterial contamination. Lab technicians dissolve the ingredients in solution, apply it to a food source in a petri dish, then incubate the dish for 72 hours to encourage any existing bacteria to grow. Then they draw samples and examine them under a microscope. If those samples are bacteria-free, the ingredient moves on to the second phase of testing, which checks for contaminants such as lead, arsenic, mercury, and cadmium. This machine, called a spectrometer, injects the ingredient solution into a plasma flame. Then, by reading the changes in light wavelengths, analyzes the chemical composition. If the ingredient is contaminant-free, it gets the go-ahead. The gel cap is made entirely of natural ingredients. Gelatin derived from beef bones, palm oil glycerin, and purified water. The proportions are top secret. An industrial blender combines the three ingredients to a uniform consistency, then heats the mixture to 175 degrees Fahrenheit. A vacuum sucks out the air bubbles as this now ready gel material flows into a holding tank. Simultaneously, they prepare the medicine fill, in this case, vitamin D. They combine it with soybean oil to adjust the potency to the specified strength. Meanwhile, they maintain the gel cap material in the holding tank at 140 degrees Fahrenheit to prevent it from prematurely solidifying. Even the hose leaving that tank is wrapped in heater tape to keep the gel liquid. A separate hose feeds the vitamin D solution from another holding tank down to the production floor as well. This hose doesn't require heating because vitamin D and soybean oil don't solidify when cool. On the production line, two stations simultaneously spread a thin layer of molten gel across a cooling drum. The gel hardens into a solid yet malleable sheet, about the thickness of cardboard. Each sheet passes over a rotating die with capsule-shaped cavities. Just before the two gel sheets come together, pumps inject the required quantity of vitamin D solution into each cavity, the pressure pushing the gelatin into the cavity. At the same time, the machine heats the gel sheets so that when they meet, they adhere to each other, forming full capsules with the vitamin D solution sealed inside. In the final second, the die's sharp edges slice the gel caps free, and they fall to a conveyor belt below. At this point, the filled gel caps contain a fair bit of moisture, so they're quite soft. If they lay on a surface too long, they'd flatten. So the conveyor belt whisks them very quickly into a rotating drum, where they tumble in slightly cool, dry air for about 3 hours. This removes enough moisture to make the gel caps hard enough to lie on a surface without flattening. After exiting, the gel caps move into a second dryer, where, spread out on trays this time, they dry for about 36 hours. After that, the gel caps are hard enough to be safely packaged. The gel caps, the ones being packaged here contain flax oil, travel down a series of vibrating plates, which progressively line them up in single file. As they pass by, electronic eyes count out the number of capsules per bottle, triggering the filling mechanism to collect that quantity and release it into an empty bottle. The next station applies a plastic twist cap. Then the bottles move onward, each one plowing directly into the center of an adhesive-backed label, which rollers then apply around the sides. Before shipping, the Quality Control Lab tests random samples from the production batch to verify that the gel caps meet all specifications. It's a playground staple, a stationary ride-on cartoon animal that bounces up and down and rocks back and forth, courtesy of a huge spring underneath secured into the ground. The bouncy coil base is what gives this type of playground equipment its name, a spring rider. The spring rider is a playground favorite. To withstand years of rambunctious riders, it has to be solid and durable. Yet for a toddler to be able to rock back and forth, it can't be too heavy. That's why the spring is made of thick steel and the animal of lightweight aluminum. That sand core is comprised of two halves, each made with an aluminum mold, duck-shaped in this case. Workers fill it with sand and adhesive mix that sets into a solid block. They insert several steel support rods, fill to the top, and even out the surface. Then expose two hooks they'll later grab to extract the core half, once the sand hardens in about 20 minutes. Meanwhile, other workers use an aluminum pattern to make each half of the duck casting mold. After applying a powder release agent to prevent sticking, they cover the pattern with a sieved mixture of sand and clay. They mount a frame around the pattern to contain the sand as they add more and more, repeatedly packing it down in all areas with a pneumatic ramming tool. Then they remove the frame and cover the sand with a wooden board. This provides a hard surface for the press, which now applies the weight of about 4 mid-size SUVs. Then they flip over the mold and remove the pattern which formed the mold cavity. The sand is now so firmly compacted that it holds the shape. One half of the sand mold has channels through which the molten metal will flow into the cavity. Workers now position several 1/4-inch thick foam spacers in the cavity and place half of the core on top of them. The spacers elevate the core, creating a 1/4-inch cavity between core and mold. The other half of the core goes on top. After placing spacers on top of that to create a 1/4-inch gap on this side as well, they carefully lower the other half of the sand mold. Now they're ready to cast the duck. The melting point of aluminum is just over 1090 degrees Fahrenheit. However, they heat much higher, to 1400 degrees, so it'll flow faster and fill the entire cavity before beginning to solidify. They pour the metal through holes on top. It flows through the runners into the mold cavity, which is that 1/4-inch gap surrounding the duck-shaped core. About 20 minutes later, the metal has cooled and solidified. They break the mold apart on a vibrating sieve, releasing the aluminum duck and shaking out the core sand through a hole at the bottom of the duck. After cutting off excess aluminum that hardened in the runners, they grind down the seam, which formed in between the two halves of the mold. Next, they weld on aluminum handles for the child to grip when riding. These handles are cast in sand molds just like the duck. Workers grind down the weld and any sharp edges, making the entire surface nice and smooth. Next, a coat of polyester powder in bright rubber ducky yellow. Then a 20-minute trip through an oven to bake the coating, making it ultra-durable. Now, delicately airbrushed with the urethane enamel paint, the details that bring Mr. Duck to life: his feet, wings, bill, and eyes. The thick coil that makes this a spring rider is made of a flexible type of steel. They bolt a steel spacer plate to it, then hide the bolts under an aluminum cover. After attaching a footrest, steel again, they bolt the duct to the plate. All these parts, like the duct, are painted with baked-on polyester coating. The spring bolts to a concrete block buried underground. Ducky and Friends are designed to withstand even the harshest winters, letting children enjoy a little spring all year round. Early versions of pancakes were thin like crepes. By the 1780s, American cooks were adding a leavening agent for a fluffier, more filling pancake. That's when pancakes transitioned from side dish to main course for the first meal of the day. Call them hotcakes, griddle cakes, flapjacks, or pancakes. There's nothing like a heaping helping of them splashed with syrup. And with frozen pancakes, whipping up some for breakfast has never been easier. Pancake production starts off with the leavening agent, the baking powder. They combine salt, whey, and various flavorings in a big blender to create a dry ingredient premix. Since these will be buttermilk pancakes, they add powdered buttermilk for flavor. They now pump liquid ingredients from storage tanks into a huge blender. These include water and eggs, sweet cream, liquefied sugar, and soybean oil. They add the dry premix and flour until the batter reaches the desired consistency. An employee tests the batter's viscosity by pouring some in a device with a little gate. He opens the gate and measures the flow down a ramp. If it runs too thick or too thin, it won't produce pancakes that are the desired diameter and uniformity. The pancake batter passes the viscosity test. They release the batter from the holding tank, and it flows into a depositor system. The depositor has 9 nozzles. Each nozzle shoots an exact amount of the pancake batter onto a hot moving griddle. Because of the perfect viscosity, each deposit of batter radiates out to form a neat round shape. Each one the same size as the next, about 4 inches in diameter. They run 3 depositors and moving griddles simultaneously to produce 750 pancakes a minute. That's an incredible 45,000 pancakes an hour. After several seconds on the griddle, one side is cooked. So automated stainless steel spatulas flip the pancakes over. There are 2 sets of flippers. After flipping, the first set repositions and the second set flips the next row of pancakes. It's mechanized synchronization. The flippers are spaced apart exactly as the depositors are, so the pancakes arrive at the flippers in the correct order to be picked up and turned over. Once flipped, the pancakes continue along the cooking conveyor and the other side is cooked. It's a short ride for these pancakes to be completely cooked. From dollops of batter to uniformly rounded and cooked pancakes, this process has taken just 90 seconds. The pancakes somersault off the cooking griddle and over a roller to land on the next conveyor. This somersault exit has a purpose. It keeps the pancakes from folding over so they land flat. Hot off the griddles, the pancakes cool down on the ride as all 3 production lines merge and head into a freezer. Inside the freezer, it's a very frigid -18 degrees, and the pancakes freeze fast. Now it's over to the packaging line. This is where the uniformity of these pancakes pays off. Their similar diameter means they can be neatly packed in groups of 6. Machinery seals 2 stacks of 6 frozen pancakes in one wrapping. It has taken less than 5 minutes to prepare, freeze, and package these pancakes. At home, prep time in the microwave should be mere seconds. Just add syrup, and this story has a sweet ending. Natural rubber comes from the milky sap of a tropical tree. Thousands of years ago, the native people of Central and South America discovered that the hardened sap was elastic and bounced. They played games with the balls of sap. When European explorers came along, it was soon a whole new ball game. Today, we make thousands of useful things from the fluid that circulates through rubber trees. Everything from tires, to balloons, to boots. The seeds are sown on plantations like this one in Thailand. It takes several years for the rubber trees to mature. Then the sap is ready to tap. In the coolness of the morning when the sap flows freely, the farm worker slashes the bark with a hooked blade. The sap oozes from the abrasion. It spills onto a metal spout inserted below the slashed section. The spout funnels the sap into a ceramic cup below. It flows for about 5 or 6 hours, partially filling the cup. They wait a couple of days for the tree to recover and then tap another section of the tree. After straining impurities, they pour the rubber sap into a plastic tub. They add formic acid and swish it around. The acid causes the sap to coagulate. After 15 to 30 minutes, it thickens to the consistency of tofu. This tofu-like sap has a sticky structure that allows it to now be rolled out like dough. The rolling squeezes out excess water and leaves a rib pattern on the sheets that increases the surface area to hasten drying. Then they rinse off the formic acid. They hang the rubber sheets to dry for about 5 hours. As they dry, the rubber thickens and becomes stronger, and the color darkens. The coagulated rubber sap has been transformed. In a few short steps, it's gone from a liquid to a solid. Workers pile the rubber sheets onto pallets and weigh the load. There's a little over 1.5 tons of rubber in this stack. They store the stacks in a warehouse until the next stage of processing. When they're ready to move on, workers peel each sheet from the stack and soak them in water for about 20 minutes. This washes away some of the surface contaminants, but not all. The rubber sheets then go into a machine with many brushes that scrub off more of the dirt. After one more rinse, the rubber sheets are squeaky clean. As you can see, the color of the rubber sheets vary somewhat, depending on the tree they came from, their thickness, and other factors. They hang the sheets on racks to drip dry. Next, they build a fire in a brick oven and smoke the rubber sheets in a chamber overhead for 5 days. It's a slow, low-temperature smoking that preserves the sheets to prevent the growth of mold. After smoking, they clip out contaminants like bark or insects that have become embedded in the rubber. In many cases, they can't get it all. They grade the rubber sheets by examining them against a bright light. Sheets with fewer remaining contaminants receive a higher rating and will command a better price. They stack the sheets according to the grade. And then it's into a hydraulic baler. It presses the stack of rubber sheets into cube form. The dimensions of the cubes conform to international packaging regulations, so they'll fit neatly into containers for shipping. They spray the rubber cubes with a mix of calcium carbonate and solvent. The mixture forms a film on the cubes that prevents mold and keeps them from sticking together during transport. This rubber is now ready for the next factory and the next transformation. It could become almost anything. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at sciencechannel.com/howitsmade.